Okay, good morning. So last lecture today, and we're going to have a series of revision sessions from today in the afternoon. If you want to come, even if you are not enrolled on the Thursday prep, you're welcome to come. There were not so many people yesterday. There are actually only few, and I think that they benefited a lot. We spent 2 hours. And many of the questions that I was asked were very similar to the questions that will appear in the exam. So if you spend time asking questions and really making the effort of understanding how I solve them, you will be ready for the exam. Now, I originally said that I will do a 3-hour session on the 11th. Some people told me that they have an exam or that it's not convenient for them, so I thought that we might as well do 2 sessions of 1.5 hours, one on Tuesday the 10th at 2 o'clock from 2 to 3:30, and I think it will be here. I need to get confirmation on the booking, on the room booking. I will send a Blackboard message, and the other session will be on the 11th. That's Wednesday between 2 and 3:30. Okay, so plenty of opportunity to ask questions and make sure that you know all the how the previous exams are solved. Okay, so we get back to the last part of the lecture material, and that is the geometrical analysis. This is an important slide because it shows the relationship that we have in an overturned fold, or fold with an inclined axial plane. And that will be the basis for the outcrop interpretation that we will do. So I'll just go through this slide again. What we basically see here is that there are angular relationships between bedding and cleavage. That is the important thing. The cleavage is everywhere dipping 60 degrees to the west, and it is everywhere doing the same because we have only one generation of folding. The cleavage is parallel to the axial plane of the fold. It is also indicating the orientation that is exactly perpendicular to the maximum shortening. So we know that this is the XY plane of the strain ellipse width, and it shouldn't really change anywhere. I mean, we can get, of course, fanning, we can get refractions, all these kind of things, but in average, it should be it should have a consistent orientation unless it was affected by a subsequent generation of fold. So that's good, and because of that, we get those relationships that basically showing that in the right way up limb of the fold, structurally right way up limb of the fold, the cleavage is steeper than the bedding. In the overturned limb, the cleavage is shallower than the bedding is steeper than the cleavage, and at the hinge, the cleavage will be perpendicular to bedding. So every time we go to the field, we find that there are orthogonal relationships between bedding and cleavage. We think maybe we're at the hinge of a fold. The other thing that we talked about is the stratigraphic facing. So that was the structural facing, whether we are at the right way up or overturned structurally. The stratigraphic facing is really related to what is young and what is old. So unless we can determine that from sedimentary features, we can't work out whether the fold is an anticline or a syncline. So here we see the younging to the top. So normal younging, this is right way up, and here the younging is to the bottom. So overturned limb stratigraphically, and therefore this is an antiform and an anticline. Okay, so that's really important. And the important thing that in the field we can go and basically ask ourselves, of course we can talk about younging, but we can also look at the structural relationships between bedding and cleavage. We look in outcrop 1, and we see that the cleavage is steeper than bedding. We know that we are in a right way up limb, and we can take the cleavage when we face the fold down the plunge, and we need to be consistent with that. So we look down the plunge, and we take the cleavage, we rotate it to bedding, and we determine that there's the kind of rotation that we do by that is clockwise rotation, or we say vergence to the east, so the upper part is going to the east. So that's basically the kind of little field exercise that we always do, and it helps us basically it tells us where is the closure of the antiform, where is the next antiform. Okay, that's the strength of that. And the reason I show this slide again is that unless you understand that, you will not understand the next 20 minutes when we talk about what we do in, exactly in the outcrop. So the cleavage here is shallower than bedding. We already said that it is structurally overturned. And again, we take the cleavage. We always take the latest generation. The cleavage is later than bedding. We take the cleavage, we rotate it to bedding, and now I apply counterclockwise rotation with divergence to the east, to the west. The upper part is going to the west. And the divergence, this arrow basically tells us there's an antiform somewhere here. So if I walk from one outcrop to the other, and the divergence swapped, I know that the hinge of the antiform must be in between, as you can see, of course. And in the limb, the relationships are perpendicular. I can't really determine the divergence in the limb because the angle is 90 degrees. Okay, does it make sense? You'd be able to do that in the field? What do you think? Okay. So let's see if we're able to do that from this photograph. Yeah, that is a typical kind of outcrop. We can take a photograph and we can put our compass and measure a number of features, mainly basically the bedding. So we all see the bedding here, and the cleavage. Okay, so the cleavage is at a low angle to bedding. And of course, from the photograph, we see only the strike. This is like a platform. So what we see here is the strike orientations. What we really need is to take a measurement and look at the deep and deep direction of the bedding and the cleavage. Okay, so let's see what kind of information we can get from a single outcrop that is cleaved. And our assumption is that the cleavage, that the foliation is an axial plane cleavage. Yeah, unless we make this assumption, then whatever we talk about, the discussion on the larger scale faults is kind of irrelevant. So first of all, we can map. Yeah, we can create a map of the outcrop. Yeah, as we said, this is a platform, so it is a map view. We have a node arrow. Always when we have a map, we put the node arrow. And we can create a structural map similarly to what we did in Shorncliffe. Now we do have cleavage here in Shorncliffe. We didn't have, but we can take orientations of bedding and cleavage, and we see that the bedding is steeply dipping 80 degrees to the west, and cleavage is moderately dipping 60 degrees to the west as well. Can we work out the intersection relation?
Yes.
We definitely can, because if we have the bedding and cleavage, then we can see how they intersect. So of course we can go around the outcrop and look for the lines of intersection. Yeah, there will not be, or on the map view, they will appear as a dot. But if we look at the 3D, we should be able to see if the bedding is penetrative, and it is. I mean, you can see penetrative bedding everywhere. The cleavage is penetrative as well. Then the intersectionation will also be penetrative. So if you go around the outcrop and we look at the lines of intersections, we should be able to stick our compass and take the measurement of the intersectionation. Alternatively, we can take those two planes and plot them on the stereonet. Okay, so all we need is just the intersection of two planes. We all know how to do that, and we can use like an app on our mobile phone that will do that for us. There are plenty of tools like that. So even in the outcrop, we can take a measurement. We can calculate it with our iPhone, and we can make sure that we get consistent results. This is what we get for these two. Yeah, we plot the cleavage here, we plot the bedding, and we get intersection of 39 to 342. So that is the intersectionation. We worked it out. That's excellent. Okay, now the other thing that we added here, so the map becomes a little bit better. We added here an arrow showing the intersectionation. Okay, we have intersectionation, cleavage, bedding, and we really create something that looks like a neat geological map now. So let's see what we get from this map. First of all, the map obviously tells us that the local orientation of bedding is 80 to 260. That's the kind of question I ask in the exam. They are trivial. Yeah, it's really trivial. I mean, you have a map here. There's a node arrow. There's dip and strike here. And I tend to ask like many small questions. And the first one would be, but what is the orientation of bedding? And for some reason, I don't know, 30% of the students get it wrong. And I think that many times because they don't think that this is actually a map. So they get, I don't know, they think that it's a cross-section and the bedding is dipping steeply to the east. I don't know what, I really don't understand why, but as you can see, it is trivial, yeah? 80 degree to 260, you need to work out from using a protractor or just give me an approximate. It's obviously not 270, it's something that is low angle from 270. Okay, so please make sure in the exam that you know, many of the questions will be almost trivial, particularly those that at the beginning of each question, of each section, and don't think that there is any complicated trick there. Okay, so similarly, the local orientation of the axial plane, so we have an axial plane cleavage, it would be 60 to 280. Yeah, so moderately dipping to the west as well. And the local orientation of fold axis is the intersectionation. So here we already need to know that the intersectionation basically tells us something about the local orientation of a fold axis. Okay, that's an important thing that we think about those relationships. Here we have a fold. We don't see the fold, but we see that there is a cleavage and there is the bedding. We are somewhere at the limb of a fold, but everywhere the intersection of bedding and cleavage will give us basically an orientation that is parallel to the hinge of the fold. Okay, it will give the orientation of the fold axis. So that is already the a little bit more advanced interpretation, but we can do a lot more. We can think already. So we know that there are folds. We know the local orientation of the fold axis. We also know the local orientation of the axial plane. So basically we know everything about this fold orientation in the same way that we did in Shorncliffe. We worked out the fold hinge from the beta axis. We worked out the axial plane, not from cleavage, but from the stereonet and the map. But once we had this information, we could think, what do we call this fold? Is it an upright horizontal? Is it a recumbent fold? So we use the classification diagram. And what do you think we call this fold? So the cleavage is well, let's start with a plunge. It's plunging 39 degrees. So what is that? Yeah, moderately plunging. So that will be the first part of the name. And it is, the axial plane is dipping 60 degrees. So that moderately or steeply inclined. Don't remember exactly where the boundary was. Okay, moderately inclined, moderately plunging. So not a very elegant name, but that's what we call these folds. Okay, but again, there's a lot more that we can say. We can think about divergence relationships. So we did that before in the cross-section where we saw the fold. Now we don't see the fold, and we can do divergence. So the important thing is that we do that when we look down the plunge. Are we looking down the plunge now? Yeah, we look, the plunge is to the node. We look, the node is basically away, we look up the node. So we are in the right orientation to do the divergence. Okay, so it's just a matter of consistency. We always want to look down plunge and determine if we say that the divergence is to the west or to the east, it's always while we were standing down the plunge. So you see that the plunge is going away from us. Right? That's an important thing. If the folds were plunging to the south, we can still do the divergence, same thing, but then swap it, basically saying we go to the east, so it actually means to the west. a little bit confusing perhaps, but I think there will be one slide when the plunge is exactly opposite. We'll see that. So plunging away from us, we take the cleavage and we rotate it to bedding. What would be the divergence? To the west. Yeah? So cleavage like that, and I rotate it, what is that, counterclockwise. Okay, so that's the cleavage, that's the bedding, and that's the rotation that I applied. Okay, so there's divergence to the west. That's all good. I made the map smaller so we can think about the larger scale. How does it sit? Where does it sit relative to a larger scale fold? And I've mentioned many times that I don't know the scale of the fold. It could be just a fold that is just a little bit larger than the outcrop, or it could be an enormous fold. The only way for me to determine that is by mapping. But there is a larger scale fold here. Otherwise, we will not get the axial plane cleavage. So first of all, where are we relative to the fold? Are we at the hinge or the limb? Yeah, definitely the limb, because the angle between bedding and cleavage is a low angle. In the hinge, we'll get perpendicular relationships. Yeah, in the limbs, we can also get parallel relationships. If the folds are isoclinal, for example, so bedding basically becomes parallel to cleavage. So either parallel or oblique would give us the limb. So we are at the limb of the fold, and we ask ourselves, where is the nearest antiform? We already answered that really. Yeah, the nearest antiform is where the divergence sent us to. Yeah, so the divergence sent us to the west. So I said there is an axial plane here of an antiform. So that is the real axial plane of the fold. And as I said, it could be here, it could be here, it could be here. It's somewhere to our west. It will have the same orientation as the axial plane cleavage. Right? So it has to be oriented like that. The only thing that I don't know is where, and I know that it is an antiform. Okay, and the next thing that I know is the sense of map closure, because an antiform will have the plunge going away from the structure. I know what the plunge does. The fold is cylindrical, so the plunge is going exactly in the same orientation that I got from the intersectionation. So the only way, so if I know the axial plane, I know the plunge direction, then I know that the closure must be in that, creating that pattern on the map view. Yeah, the plunge is going away from the structure. It cannot go into the structure because that would be a cylindrical form. Okay, the divergence always is sending us to the next antiform. Okay, and mind you, you could have, if you thought about the relationships, you could have worked it out without using divergence, just using common sense. But the good thing about using these little tools is that even if you don't see the structure, you know, some people just immediately kind of see the relationships and say that, of course, there must be an antiform closing like that. That's the only way to solve, you know, to make a fold with an axial plane like that, and that will plunge in that direction. Some people will immediately see that, but many people don't. You know, you're out in a field, all you see is just a little fragment of a fold. You don't even see the fold, and these tools will help you basically making decisions, saying there has to be an antiform in that direction. An antiform is plunging away from the structure, therefore the pattern of the fold must be like that. Okay, so we know the sense of map closure, and we can still obtain more information. So we talked about structural facing. So again, we look at our map and the cross section that we have here. Where are we? What do you think? Is that limb structurally overturned or right way up? Overturned because the bedding is steeper than the cleavage. Okay, so we think about those relationships. That's exactly what we got here. bedding is steeper than cleavage. They both dip in the same orientation. They dip in the same orientation everywhere, but here the bedding is steeper than the cleavage, so that is structurally overturned. And we can talk about the stratigraphic younging as well, because if we look carefully at the rock, we see that there is a pattern here of gray and white layers, and the transition from gray to white is gradual. That basically is the effect of graded bedding. So what I think I enlarge it a little bit. So what really we see here is our coarser grains that gives us the white color, and then the finer grains are blocking the light and creating darker colors. That's very typical for graded beds. Okay, and you see that like a gradual transition, and that basically tells us that this is that the younging has to be to the east. So what does this mean in terms of younging? Is that if the younging is to the east, the layer is dipping to the west, younging in that direction. Is that overturned or right way up? Yeah, overturned. So it is whatever antiform we found there, that was also an anticline. Okay, so if we are at an overturned limb stratigraphically and structurally, then our antiform will be an anticline and the synform will be a syncline. Yeah, surely the synform will basically be here, right? So we could continue. I mean, maybe you are more interested in synforms, so you say if I want to go to the next synforms, I need to walk to the east. Yeah, many times in the exam you will find the questions spelled out like that. Like if you want to find the closure of the next synform, would you walk? Where would you walk? So what you would need to say, I will walk to the east. Yeah, this is where I will find, or I will need to walk to the southeast. If I want to find the closure of the next antiform, I will walk to the northwest. And you can do it either by walking along. So we can think about the closure of the marker layer. So we have here the red marker layer. So if I want to find where it is closing, I need to go to the northwest or to the southeast. Or we can think about doing a transect. If I do a transect and keep walking to the east, what would I find? I will find basically the hinge of the next synform. Or here I will find the hinge of the next antiform. Okay, so there are two ways of doing that. Either follow our marker layers that will close, or doing a transect and basically moving from one hinge to the other. Okay, so we got the younging, and that's about it. So a lot of information from one outcrop. If we do that consistently, moving from one outcrop to the other, we basically understand the whole geometry of the fold, and of course the scale as well. One more thing that I want to mention is that you don't always need to look at cleavage and bedding relationship. The minor folds will do exactly the same job. So here are minor folds. They are S folds, and in order that you can have S or Z folds, they will give you some sense of asymmetry. They essentially give you divergence. Divergence is the sense of overturning, right? So you see divergence. You can do divergence also by just looking at the axial plane of the fold relative to the enveloping surface. It does exactly the same thing. If we have M folds, we don't have any divergence. Basically, the relationships are symmetrical. The axial plane of the fold is perpendicular to the enveloping surface. So you can see here, this is basically identical information. Here we have the axial plane of the fold oblique to the enveloping surface. We have here the bedding oblique to the cleavage. And what is divergence? So this is a tricky one, because you see that the fold plunge is plunging to the south. Here again, it's a map, and the fold plunge is plunging to the south. So you need to be careful when you make these observations. You say that I'm actually looking now up the plunge. Yeah, it's plunging to the opposite direction. So whatever versions I get from here, I will report the opposite. Yeah, in my notebook, I will actually write the opposite. So I see a vergence here, like to the east, right? So I will indicate that this is west vergence. So the next antiform is going to be to the west. And the same here. I take the cleavage, I rotate it to bedding, gives me vergence to the east, but in fact, I will indicate vergence to the west because I'm looking. You basically get a mirror image if you look down plunge or up plunge. Okay, so and again, when I talk down plunge or up plunge, basically means if you look like that, now you guys looking up plunge, and now you're looking down plunge. So here is the cleavage, the bedding, that's the vergence, and the vergence is to the west. And that is the vergence here, vergence to the west. Okay, so it gives us exactly the same information. And lastly, I think that's the last slide before I have a number of summary diagrams, is that you can think about, you can do these kind of things at all scales. You can use individual outcrops and map them and understand the whole picture, or you can sometimes see the whole picture from distance, you know, just thinking about what you see here. This is the bedding, going like that, and that is the cleavage. Yeah, that is the axial plane cleavage. And if the intersection, always a little bit hard to think about the intersection to see the intersection in a two-dimensional view, but let's assume that the intersection is horizontal. So we immediately know what type of folds are present here. The axial plane is shallow, right? The hinge is horizontal. How do we call these folds? Axial plane is shallow, so we can take a piece of paper and saying what we actually see here is something like that. The axial plane is shallowly dipping to the right, yeah, recumbent folds. Okay, so bedding, cleavage, or axial plane. It's not really cleavage that we see, it is the axial plane. And we immediately go to our classification diagram and we think there are big recumbent folds here. Okay, any questions? Okay, so let's move to a number of summary diagrams, just first of all on geometrical analysis and then in general on the major concepts that we learned in the course. So we talked about Younging, and Younging basically gives us information on whether we look at anticlines or synclines, and we can look at stratigraphic facing of a certain outcrop and work out whether we are in the right way uplimb or overturned as far as the stratigraphy is concerned. Right? So in right way up, the Younging is upward, overturned, the Younging will be downwards. And unless we learn how to see sedimentary features, we are unable to do that. Vergence is basically a structural usage. It will not help us with the stratigraphy, but it will tell us what is the structure, whether it's an antiform or a synform. It can tell us the relationships of the bedding and cleavage, and whether we can do vergence or we can't. Will tell us if we are at the limb of or a hinge of a fold. In the limb, the cleavage is oblique or parallel to bedding, and in the hinge, the cleavage is perpendicular to bedding. And in terms of facing, we can determine whether we are at the right way up limb or overturned limb based on the cleavage bedding relationships. Cleavage is steeper than bedding in the right way up limb and is shallower than bedding in the overturned limb. Okay, so I hope that this is all quite clear. It is really not very complicated, but the important thing is that you don't memorize it, but you create, you know, the diagram of the big scale fold, and you think about those relationships and you see where it comes from. Axial plane cleavage will give us information over the fold axial plane. That's simple enough. And the intersectionation gives us information on the fold hinge. So that's something that maybe is less intuitive, but it is extremely useful. And In terms of kinematics, we need to remember that some of those structures give us information on strain. So when we have folds, the axial plane of the fold is always perpendicular to the maximum shortening. Therefore, the axial plane cleavage is the xy plane of the strain ellipsoid. If we have stretching lineation, we know that this is in fact the x direction. So if we have combination of cleavage and stretching lineation, we know everything about the orientation of x, y, and z. The intersecting lineation does not give us any information on strain. It gives us only information on geometry, but it's not necessarily will be parallel to any principal stretch axis. Okay, so if you don't have any further questions on geometrical analysis, I will briefly go through. I tried to summarize the most important concepts and terms and relationships between concepts and terms that we cover during the semester. There's a fair bit. Yeah, it's not it's quite dense, but I think there are about 6 slides here. And if you are able to tick each one of those and make sure that you fully understand them, I think that you are pretty much ready for the exam. So the important thing, first of all, that we have, as far as strain and flow is concerned, we have a number of terms and concepts that we really have to understand what they mean. If some of these terms are vague, then you need to make sure that you understand them. Instantaneous stretch axis. So we have always an orientation. During deformation, we always have an orientation that is stretched most and an orientation perpendicular to it that is shortened most. Yeah, and that happens instantaneously. When we looked at rocks, we never looked at the instantaneous deformation. We always look at the finite strain. But in order to understand where the finite strain came from, we had to go through that, think about the instantaneous stretch axis, and think about the flow hypothesis. So where material, what is like a single particle that you put, for example, in the rock or in whatever you deform, what is the tendency of this particle? What are the orientations that this particle tends to flow? And we see that we can have all sorts of different flow patterns. The end members were pure shear flow and simple shear flow. In simple shear flow, their flow hypotheses were very simple. It was like a highway. Yeah, particles moving to the left and to the right here, or to the right and left here, depends if it's dextral or sinistral, simple shear. In pure shear, we got kind of hyperbolic trajectories of flow. So that was flow. It is not mentioned in all textbooks, and I think that it is a mistake, because unless you understand flow, you can't understand strain, in my opinion. So then we talked about coaxial flow and non-coaxial flow, and really the important thing is that coaxial flow is a flow in which the instantaneous stretch axes are parallel to the flow hypothesis, and non-coaxial flow is a situation where the instantaneous stretch axes are not parallel to the flow hypothesis. And therefore, this type of flow will always have rotations. Every orientation that is stretched, for example, the orientation that is stretched most instantaneously will immediately rotate, and there will be another orientation that now is stretched most, or another line. So this is non-coaxial flow. Pure shear, simple shear are the two end members, and in between we have a whole spectrum of flow that we call general shear. So basically combinations of pure shear and simple shear. We talked about principal strain axis, X, Y, and Z. X is the maximum stretching, Z is the maximum shortening, and that could be described either instantaneously or in a finite strain. So we can have an instantaneous strain ellipsoid, which is made of all these 3 axes, or the finite strain ellipsoid. And each 2 axes make a plane. So when I say the plane XY of the strain ellipsoid, I basically mean the orientation perpendicular to the Z direction. Okay, so the important relationships is that in pure shear, the instantaneous Stretch axes are parallel to the flow hypothesis. We get coaxial strain. In general shear, the relationship is oblique, but not 45 degrees. In simple shear, it's a special situation where the relationship is exactly 45 degrees. And both of these will give us non-coaxial strain. Okay, then further in terms of strain, we talked about the definition of strains. So longitudinal strains, we have 4 different little equations to describe longitudinal strain. And many times, if you are asked a question in the exam to calculate the longitudinal strain in the z direction of, say, a deformed mountain belt, for example, a fault, bend fault, yeah, there is certain shortening, you are asked to present it normally in terms of stretching and in terms of elongation and percentages. The elongation will give you the percentage if you multiply the value by 100. Okay, so 0.8 shortening, z is equal to 0.8, is equal to 20% shortening. Okay, so make sure that you're familiar with the definitions of longitudinal strain. The other strain measures that we talked about are shear strain and volumetric strains. We talked about strain in 3 dimensions, 3-axial strain, and in 2-dimension plane strain. And simple shear, for example, is a situation where we actually have strain in 2 dimensions. We essentially move one block relative to the other, and material is not moving in the 3rd dimension. So we have strain in 2 dimensions. Constrictional strain, oblate strain, and tectonites. So we talked. These are all expressions of 3-axial strain. So strain in 3 dimensions. So in terms of the relationships between the concepts, longitudinal strain, we define 4 different measures for that. They're all the same. They're just different kind of slight variations. And shear strain, volumetric strain. And in terms of the strain ellipse, we saw that the 3-axial strain can give us either constrictional strain or oblate strain. So in terms of tectonites, so rocks that show that their grains actually internally represent a strain, are either elongated, forming L tectonites, so sausage-like structures, or hamburger style flattening, so dominated by foliation, dominated by stretching lineation. And in plane strain, we'll have something in between. So is that okay, or you feel that it's from the far past and it doesn't? Yeah, no, that's good. Okay, we talked about mechanics, and in terms of mechanics, the important thing to know is what's the definition of compressional stresses and tensional stresses. Compressional stresses are positive, tensional stresses are negative. What is the actual definition of stress? And then the definition of the principal stress axis. So the important thing with the principal stress axis is that those are the orientations in which there is a 0 shear stress. Okay, so there are 3 orientations perpendicular to each other that have a 0 shear stress, and these are the principal stress axis. And one of those will be the maximum stress, one of those will be the minimum stress, and the third one will be an intermediate one. So in a way, it's a little bit equivalent to the way we handle strain. We need to remember, though, that the concepts are entirely different. I hear many, many times students, but also professional geologists, mix stress and strain. They want to talk about strain and they talk about stress and vice versa. So it's a kind of mathematically there are some similarities in the way that we deal with them, but they mean something completely different. And we talked about the stress equations. So equation for normal stress and for shear stress, you don't need to memorize them, but what you do need to understand fully is how the stress equations are represented graphically in the Mohr circle. Okay, so that I think most people find it quite easy. Once you get a handle of it, you understand, that the one axis is the shear stress, what one is the normal stress. It's quite simple, really. And then within the Moore diagram, we can add the failure envelopes, and there are a number of different envelopes that we can define. And once the Moore circle touches the envelopes, we get failure. And this is all about fracturing. So the whole discussion is about the brittle mechanics. So there will be types of fractures forming. Fracture mode 1, mode 2, mode 3. Mode 3 are the faults that we are familiar with. So normal faults, reverse faults, strike slip faults. And mode 1 are veins. So they don't have any shear movement. They just have, it's just dilation. So, or joints. Yeah. So essentially we just open spaces. Mode 2 are in between. There's opening and a little bit of shearing as well. And then we talked about the effect of poor fluid pressure. So if we add fluids in overpressure, then the whole strength of the rock is considerably reduced. So in the Moore circle, we kind of shifting to lower stresses, lower normal stresses. Okay, in terms of the relationships, so definition of stress equations, Moore circle, failure envelope, we have three different ones that we need to understand. The Moore-Coulomb is for compressive stresses, Griffith is for tension, and together they form the envelope that you are familiar with, but you also need to understand the failure envelope for pre-existing faults. And it's a very easy one, it's just linear relationship, but what becomes complicated, and that, when I ask these kind of things in the exam, this is where people start to get a little bit confused, is that the pre-existing faults, the failure envelope will do something only if those faults exist in the right orientation. So you need to learn how to read it. It's not necessarily that the rock will fail when it touches the failure envelope for pre-existing faults. It will fail only if those faults if those planes actually exist in the right orientation to fail. And you can predict what those orientations are going to be. If they don't exist, then we'll create new faults with a Moore-Coulomb failure envelope. So then we talked about faults. So deep slip faults, strike slip faults, oblique slip faults, that's basically the whole family of faults that you can think of. The concept of net slip. So we talked about throw, about separation, different ways of looking at the displacement, but really there's only one vector that's showing the real movement, and that is the net slip. We did an exercise in the truck about that was very useful to understand that concept. Slicken lines are those lines that are parallel to the net slip, to the real movement. And a bunch of kinematic indicators, radial shears, n-echelon tension gushes, n-echelon folds. So all these normally appear in the exam in one way or other. You have a fault, and you see that there are radial shears there, and you are asked, what is the kinematics? Or you have a bunch of folds, similarly to what we saw in the Broken River map. And the orientation of the fall axial planes relative to the fault tells you what the kinematic of the fall. The tension gushes are those that people tend to get confused because they look opposite to like their appearance seems to be kind of misleading. They appear as if they show the opposite sense of movement. But if we think how they form, we realize that they actually show the opposite kinematics of what they look like. Bends and stepovers in strike slip systems will give us areas of transpression or transtension, so very useful terms to know. Transpression is basically a combination of strike slip and shortening, and transtension is strike slip and extension. Okay, in terms of the relationships, thrust, normal faults, strike slip faults, and very important to understand how these are possibly linked with stresses. Okay, so the discussion on the mechanics is kind of relevant. Depending on the orientation of sigma 1, sigma 2, and sigma 3, we'll get a normal fault, reverse fault, or strike slip regime. Okay, in terms of faults, so lots and lots of terminology. Yes, we talked about fold hinge, fold axial plane, antiform seam folds, anticline sink lines, neutral folds and non-neutral folds. What that means is basically folds that a non-neutral fold would form an antiform or a synform. A neutral fold would be like this fold. It's not an antiform, it's not a synform. The names of the folds, upright, plunging, recumbent, recline. So for the classification diagram, there are others as well. For the tightness, roundness, so that's all about the style. The classes of folds, so class 1, 2A, 2B, 2C, class 3. The processes, so of buckling, so buckling by flexural sleeve or buckling by neutral surface, so the sponge versus the telephone directory. We talked about bending, so basically rather than buckling we just bend. And we talked about disharmonic folding, and the extreme case of disharmonic folding is folding that basically gives us transposition, so all the layers become basically rotated or transposed to the orientation of the axial plane. And we talked about fold amplification after buckling. So when I ran out of space for this with the sponge, I basically started to internally deform the layers, and that is the fold amplification. Okay, so the important things, when we look at folds, we look at orientation, style. We need to understand the theory of folding, and many times we start with buckling, and then after that we amplify the whole thing by homogeneous strain. And lastly, I think that's the last one, maybe not. In terms of foliation, lineations, so primary versus secondary foliations or axial plane foliation. Static cleavage is a type of axial plane foliation. The process of pressure solution, I talked a lot how we actually form static cleavage. Myelonitic foliation, stretching lineation, intersection lineation. We talked about vergence today, structural and stratigraphic facing. So in terms of the fabric elements, really the important things are foliation and lineations. But when we talk about lineations, we need to know that there are two entirely different types of lineations. There are the stretching lineations and the intersection lineations. Okay, so for geometrical analysis, what we look is at the axial plane foliation, the intersecting lineation, the stratigraphic facing, gradient cleavage relationships, all the stuff that we talked about today. For the kinematic analysis, we talk about the axial plane foliation and the stretching lineation. They will give us the orientation of the strain ellipse. Okay, that's all. You see, all these guys are so happy because they do the course evaluation. So please, if you haven't done the course evaluation, please do it. It's very important for the school because the school is going to be reviewed next year. And if we don't have response, we're in trouble. Okay, so please do that if you haven't done that until now. Okay, and that's all. I hope that, well, I'll see you in the revision sessions, I'm sure. And I hope you enjoy the course.